Okay. Okay. Good evening, guys. So let us start today's session. Let me share my screen. Okay. So I guess. Okay. I guess my screen is visible. Okay. So, okay. So check whether it's getting. Yeah. Recorded. Okay. Okay. So good evening, guys. So we'll start today's session for the course Analog Circuits. NPTEL course for Analog Circuits. The course instructor is Professor Jayanta Mukherjee from IIT Bombay. So today, and I'm Narayan PP, research firm from IIT Palakkad. I'm a teaching assistant for this course. So today we'll be solving few questions for the portion that sir has covered in week 6. So I think during the week 6, sir has covered some portions related to the filters transformation and regarding few diode circuits and all. So let us quickly see or quickly solve few questions, few collected questions for the week 6 week 6 syllabus. So let me check whether I'm audible, right? I guess I'm audible. Yeah. Okay. 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 So let us start. So let us start with the first question. So the first question is a Chebyshev prototype filter is supposed to be designed with a value of epsilon equal to 0.5. What will be the value of maximum attenuation A max? So I think some disturbance is coming in voice. Anyone has okay. 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 So the question is Chebyshev prototype filter is supposed to be designed with the value of epsilon equal to 0.5. What will the maximum attenuation A max? So what will the maximum attenuation A max? So that is the question. So let us solve this. So before that, let us just quickly revise how the Chebyshev filter transfer function or the response, magnitude response is. So as you will be remembering, so the Chebyshev filter will be somewhat like this, right? Okay, so this is 1 and this is 1 by root of 1 minus epsilon 1 plus epsilon square. And this is T of j omega is the Chebyshev magnitude, means the transfer function means this will be the transfer function, and the magnitude plot in frequency domain of the transfer function of Chebyshev prototype filter. So and there is a cutoff omega p, and this will be omega s. So what is Amax? Amax is the maximum attenuation attained at omega p, right? Maximum attenuation attained at the frequency omega p. So that is the maximum attenuation in the passband. That's it. So that is the maximum attenuation in passband. And what is and there is one more parameter, right? It's similar to the Butterworth filter that we discussed last week. So this is A minimum. So that is the minimum attenuation in the stop band. So this is the A minimum, that is seen at the frequency omega s. Okay. So we can, this is actually gain. So in dB, how
Sir,
will
excuse me.
yeah, please.
Sir, for a low pass filter, it must have minimum attenuation in the pass band and maximum attenuation in the stop band, right?
Correct. So like
But here
I understood.
it is something different.
I understood. So the actually that is like I'll tell you. I'll just take another color. Okay. So like in passband, this attenuation must be minimum, right? So what we are seeing here is the the maximum attenuation which is possible in the passband. That's it. So like definitely if this is the passband, there will be definitely some sort of attenuation, right? So like it will be reducing like this, somewhat like this. So this is a cutoff, says omega c. Though this is the DC gain, there will be some attenuation somewhat like this. Correct. So at till omega c there will be some attenuation. We don't know, some AdB attenuation. Okay, so what is a maximum attenuation seen in passband? That's it. What is a maximum? Like there will be the attenuation in the passband maximum will be say 1 dB, 2 dB, mostly it will be 3 dB, right? So what is the maximum attenuation seen in the in a particular filter in the passband? That is a max. So it is actually only denotion. It doesn't mean that is a maximum attenuation seen in the filter. That is not it doesn't corresponds to maximum attenuation of the entire filter. It is a maximum attenuation possible in the passband. That's it. Okay, and we require heavy attenuation in the stop band, right? So we can even like if we see the filter, it will goes on decreasing. So after the transition band, what is a minimum at least what is a minimum attenuation? So if I see at this frequency, this is the attenuation. If I see at this frequency, okay, at this frequency, this is the attenuation. So what is, among these attenuation, what is a minimum one? So that is denoted as a minimum. So that is a minimum attenuation in stop band. And in passband, how we'll see actually in passband, ideally speaking, there should not be any sort of attenuation. So but still there will be some attenuation. So at this point there will be some attenuation, at this point there will be some attenuation, at this point there will be attenuation. So what is the maximum attenuation possible? What is the maximum attenuation possible in the passband? That is denoted as A max. That's it. So it doesn't mean like A max means the maximum attenuation of the filter. It means only the maximum attenuation the possible in the passband. Okay.
Okay.
Okay. Okay. So let me rub this. Okay. Okay. So okay. So like if I draw this in dB, T of j omega and dB. Okay. Like I'm assuming like it will be somewhat, the shape will be somewhat like this. Okay. So so at stop band, it may start at this point or this point. So what is the maximum value here? It is 1, right? So log of 20 log of 1 is equal to 0, right? So that will be, so that's why we start with 0. Okay. And at this what is the maximum attenuation is here? It is like 1 by root of 1 plus epsilon square. So this is 20 log of 1 by root of 1 plus epsilon square. Okay, so this is actually in Chebyshev filter, this is mentioned as the maximum attenuation, A max. Okay, so if I write here A max in dB, okay, A max in dB. So I will write, so from this point, okay, from this point to this point. So 0 minus the value at this frequency at omega p. So what is that value? A max is 20 log. So 0 minus 20 log. Okay, so 1 by root of 1 plus epsilon square. Okay, so this equal to, so minus 20 log. So I can bring the denominator numerator, right? So 1 plus epsilon square power minus 1 by 2. Okay, so 1 minus 1 by 2 I can bring here. So it will be 10 log 1 plus epsilon square. So this is the A max in dB. Okay, so the question is like given epsilon equal to 0.5. So what is A max? So we just need to substitute here. So 10 log of 1 plus 0.5 square. That's it. So whatever value you got, that much dB is the maximum attenuation in the passband. Okay, similarly, though it's not asked, we can find what is the minimum attenuation in the stop band, right? So that is at omega p. So that will be 0, like a minimum in dB is equal to, so it is the minimum attenuation, right, with respect to 0. So this is the a minimum. Okay, so what will be here? So 0 minus 20 log t of the omega s. So we can substitute this omega s in the transfer function of Chebyshev filter. So on substituting that, we will get what is a minimum. Okay, so this is the question. So question is to find what is a max only. So we can find directly by substituting in this equation 20 log of 1 plus epsilon square. So in epsilon we can substitute what equal to 0.5. We'll get some value. So we'll just check what is the value. I'll show the solution. So max equal to 10 log of 1 plus epsilon square. So epsilon I substitute as 0.5. We'll get a max equal to 0.969 dB. Okay, so so that is the first question. Okay, so let me go to the next question. Okay, second question is you are
Sir,
huh, huh,
how to remember the transfer functions?
how to
Remember, sir, I'm unable to remember those.
I think that's a simple one, right? So t of
For here we have to
I
write
understood, like
for
I think you have to remember that anyway. Like if you do one or two questions or two or three questions, if you solve means I think you can remember it.
okay.
I think root of, right, root of 1 plus epsilon square to cos, I think cos.
Sir, why here cos h is coming, sir? That's transfer function.
Hmm.
And the other thing is for Butterworth, it is on the circle and here on the ellipse.
You mean circle and ellipse means in the pole, right? Pole. I think for the pole.
Yes, sir. Yes.
Like if we solve this, I don't remember how this transfer function is being how they reach to this transfer function. But if we expand this and write, I think the relation for the poles will be somewhat equivalent to the equation of ellipse. So maybe because of that, but the proof
Okay.
for that is out of scope. I can't do that. Means I don't remember how they receive means reach there. That's why.
Okay, sir. But it would be better for us if there is a
Huh.
how we arrived at this transfer function that will provide us with a good insight, right?
Correct. That's correct. But I don't know. Like I think in the class itself, sir has started with this itself, right?
Sir, that's the reason I'm questioning.
See, I too don't know correctly how they reached to this. Means I don't remember perfectly. But if you want, I will go through the materials and I will check and send to you. Is it okay? I think I have also sent the solution to one question that you sent, right? Similar to that, I will send.
Yes, sir.
Okay.
Yes.
Yeah. Okay.
Okay, sir. Could you please send that, sir, if
Sure.
possible?
Sure. I will check and send it.
Okay,
Okay.
sir. Thank
Okay.
you.
So this is the transfer function. Again, correct only for omega greater than or equal to omega p. Okay.
Yes,
So
sir. Correct.
this was the transfer function. Okay. So the second question is like you are designing a Chebyshev filter, okay, with this specification omega p equal to 10 kilo radians per second, omega is equal to 100k radians per second, a max equal to 3 dB, and a minimum equal to 60 dB. The question is to determine the value of epsilon. So in effect, I think we need to find what is epsilon and n. So in the next question, it will be like what is the value of n. So in effect, we need to find what is epsilon and n. So how we will find? I think uh, from the previous question itself we could find, right, what is A max directly. You know what is A max equal to, it is in dB. So it's given dB, so it is 10 log of 1 plus epsilon square. So from this from here itself we can find what is epsilon. So what will be epsilon, like so RHS will be 1 plus epsilon square, and this will be 10 power A max by 10, right? So what is epsilon will be equal to root of this minus 1, so 10 power A max by 10 minus 1. So this is epsilon. So already they have given what is A max value. A max is 3, so you can substitute here 3 by 10, so 10 power 3 by 10 minus 1, so root of this value. So whatever is the value, that is the epsilon. Okay, so that is this question. And the next question, in the question 2, I'll show you this. In question 2, it is to determine the order of the filter. Okay, so how to determine the order? So order is like since we found what is the epsilon value, we can substitute in this question, right, epsilon as this particular value. Okay, now only thing is like I need to find what is n. So how we will find n? We can we can utilize this value, that is A minimum. So we know right, what is A minimum in dB. So in previous question I had defined this already mentioned, like A minimum is equal to minus 0 minus 20 log of T of j omega s, right? So we need to substitute omega equal to omega s in this equation. So which value will take? Omega is definitely omega s is greater than or equal to omega p. So I need to take this equation. So if I substitute that here, I'll get 20 log minus 20 log by root 1 plus epsilon square. So this is cos h omega s by omega p. Okay, so again I can bring minus 1 by 2 outside, so I will get 10 log of this term, 1 plus epsilon square cos x square and cos x inverse omega s by omega p. Okay, so let me rub this part. Okay, so I have got this. So from here I can take anti-log. So I'll get 10 power A max, sorry, A minimum by 10 equal to 1 plus epsilon square cos x square cos x inverse of omega s by omega p. Right. So from here, so I can bring this 1 here, right? So minus 1. So this gone. Okay, I'll just rub this. Okay, I can bring this. I can bring this epsilon square also. So by epsilon square, I can bring this here. So again, I can rub this epsilon square from here. So then I can write here as n cos h inverse omega s by omega p. Okay, so what I can do is like this is square of cos h of this term, right? So this is like what is this term? So it is root of, right? So it's square, so root of cos h inverse of the LHS. So cos h inverse of 10 power a minimum by 10 minus 1 by epsilon square. Okay, so from here, what is n? N is equal to, so I can bring this down, so in denominator, so this by cos h inverse of omega s by omega p. Okay, so this is n, so this is the value n. So you know all the values of I know what is a minimum, it is being given 60, and what is omega s, that I know. Okay, it is 100k. What is epsilon, that we have found in the previous question, so we just need to substitute it and you will get some value n which is near to 3. Okay, so this is how we'll solve that. So again, as the student has mentioned, we need to know the transfer function here. Yeah, hello. Cos correct, 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 correct. I'm sorry, correct only, that is correct. That was a mistake here. So root of this is cos h inverse of this. Okay, so thanks for that. So this is how we'll find the value of n. So let me show the solution. Okay, so this is the solution. So as mentioned, so I have epsilon from the previous equation. I have the transfer function t of j omega for omega less than omega p and omega greater than omega p. So what we'll do is like so we need to find the value of n. So we'll use the data of a minimum. Why a minimum? We could have used a max, right? But for a max occurs at omega equal to omega p. So at that case, we have to take means when we take that, like this component will be gone, right? This will be equal to 1. So we cannot find what is the value of n. So instead of that, we'll use a minimum, so that this component will be there. Okay, and we'll find n. So we'll substitute omega equal to omega s, and at omega s, a minimum is equal to 60. So I have substituted that as I explained earlier, a minimum equal to 10 log of this term. Okay, and I found what is omega s by omega p and substituted in cos h inverse, so we'll get that cos h inverse of that term as 2.99. and just a rearrangement as mentioned in the just before, just need to rearrange to find what is the value of n. So n equal to 1 by 2.99 into natural log of this. Why natural log? Natural log is like since we know cos h inverse of x is given as natural log of x plus root of x square minus 1. Okay, so this is the general equation of cos h. So I just substitute instead to find what is cos h inverse, I just substituted here. That's it. Okay, so so by substituting that, we'll get the value of n equal to 2.54. So we can't make some filter with an order 2.5, right? So it should be an integer. So we can consider n to be equal to 3. So it is equal to 3. So this is how we'll find, or we'll design a Chebyshev filter with epsilon and n value. Okay, so I guess it's clear. So the question was like the parameters has been given: omega p, omega s, a max and a minimum. For the previous question, it was like what is the value of epsilon. So we just we know the a max is equal a max is means the maximum attenuation, right, in dB. So that equal to 10 log of 1 plus epsilon square. So we substitute a max 3 dB, just rearrange, we will get what is epsilon. Similarly, we need to find what is the order of the filter. So for that case, we know the transfer function of the Chebyshev filter. Okay, so we'll substitute omega equal to omega c here, and we know at omega s, a minimum is 60 dB. So substitute those values, just rearrange, we'll get what is the value of n. Okay, so that is how we used to solve this. Now coming to the next question. Next one question is, consider RC low pass filter with the cutoff frequency of 1 kilohertz. So it's an RC low pass filter with the cutoff frequency of 1 kilohertz, and if the value of capacitor for the RC low pass filter is 100 picofarad, then determine the value of capacitance required if the cutoff frequency is to be shifted to 15 kilohertz. Okay, so basically it's a low pass filter. Okay, so somewhat like this. So it's an RC phase shift oscillator. Not oscillator, low pass filter. RC low pass filter. So say this is the low pass filter C R. Okay, so and the cutoff frequency here is 1 kilohertz. Okay, so what is the transfer function of this? Transfer function T of S equal to 1 by SC by 1 by SC plus R, right? So 1 by SRC plus 1. So this is the transfer function, or in j omega terms, d of j omega equal to 1 by j omega RC plus 1. Okay, so this is the transfer function of this one. Okay, now the question is like we need to design. Okay, the value of C is being given, and we need to determine the value of capacitance required if the cutoff frequency is to be shifted to 15 kilohertz. So already it's 1 kilohertz. So the question is to design the circuit such that the filter cutoff is now shifted to 15k. Okay, and the value given here is the capacitance. So already the capacitance value is here is 100 picofarad. Okay, so we need to find the new capacitance. So I am going to replace this capacitance with a new capacitor, say C dash, and I need to find what is the value of this C dash such a way that the frequency shifted to 15k. So from this transfer function we know like 1 by, so j omega by omega p plus 1, right? So this omega p is the cutoff frequency of low pass filter. So omega p is given as from this relation. So j omega into RC, right? So what is omega p? Omega p will be equal to 1 by R into C. Okay, so what is the new frequency omega p dash? That is 15 kilohertz, right? I mean fp dash is 15 kilohertz. So what is omega p dash? We know, like we will just replace this capacitor with a new capacitor C dash. So the new frequency omega p dash we can write as 1 omega p dash equal to 1 by R C dash with new capacitance. So we just need to find, so they have not given the value of R, we know only the value of C. So we'll how we'll find, we'll just divide these two relations. So omega p by omega p dash will be equal to 1 by RC by 1 by RC dash. Okay, R cancel, so it is equal to C dash by C. So what is C dash? C dash is equal to omega p by omega p dash into C. Okay, so I know omega p, it is 2 pi into fp, and omega p dash I know 2 pi into the new frequency fp dash, that into C. Okay, so just substitute. I know what is fp. Fp is the previous frequency was 1 kilo, right? So 1k, and fp dash is the new frequency, that is 15k, and capacitance is 100 pico. So if we just substitute and calculate, we will get the capacitance value in picofarad. So that's how we'll find the capacitance value in this question. So we'll just check the solution here. So as mentioned, the given the already the cutoff frequency of the low pass filter is given, and the new cutoff frequency also given, and we know the transfer function, general transfer function of a low pass filter given as this, with omega p equal to 1 by RC. Okay, and also we know if the capacitance is replaced with a new capacitance, omega p dash will be equal to 1 by RC dash. I just divided these two terms and we got C dash equal to C into omega p by omega p dash, and on substituting the new capacitance that I need to connect instead of C is 6.67 picofarad. So if I connect such a capacitance, I will get the cutoff frequency of the new low pass filter as 15 kilohertz. Okay, so that's it. That's all about the fourth question. Okay, now coming to the fifth question. Fifth question is the transformation of a low pass filter into a high pass filter is shown in figure. Okay, so this will be this is a low pass filter, right? So this is the low pass filter, and this is transformed to a high pass filter. Okay, so if the C is equal to 100 picofarad, so C is 100 picofarad, the cutoff frequency of the low pass filter omega is given as 5 kilo radians per second. Okay, and the cutoff frequency of a high pass filter is given as, say, so I will denote as omega L for low pass and omega H for high pass. So omega H equal to 20k radians per second. So what will the value of inductor L? So that is a question. So given the capacitance C value, what will the value of L if the cutoff frequency of both low pass and high pass is given? Okay, so that is a question. So how will find that? So in we already know how like if I have a low pass filter, okay, if I have a low pass filter, I can transform to high pass filter, right? We just need to substitute the value of omega equal to, so what was the value? Omega equal to the low pass filter cutoff frequency into high pass frequency by omega. J omega equal to omega L omega H by j omega. So if I substitute that, we can transform this into a high pass filter, and just need to relate. So instead of that, we'll try with the transfer function itself of both the filter. Okay, so here if I write the transfer function of this filter, what will be transfer function? It will be equal to u of j omega will be equal to 1 by j omega rc plus 1. Okay, and what will the transfer function of this? T of j omega to j omega L by j omega L plus r, right? So j omega, so I'll do one thing, I will take r outside, so j omega L by r by j omega L by r plus 1. So this is the transfer function of high pass filter, and this is the transfer function of low pass filter. Okay, so what is the cutoff frequency of a low pass filter here? Omega L is given as 1 by RC. And what is the cutoff frequency of high pass filter given? Omega H is, from here it is like by omega H, right? So omega H is equal to R by L. So this is the higher cutoff frequency of the cutoff frequency of high pass filter, and this cutoff frequency of low pass filter. So here they have given only value of C, right? So I can substitute the value of R from this equation. So R is given as R equal to L into omega H. Okay, I can substitute this here since R is not varied in for the both the filters. So omega L equal to 1 by R is given as L into omega H into C. Okay, so we need to find the value of L. So we'll just take L to LHS. So L equal to 1 by, so I will bring omega L to RHS. So omega L into omega H into C. So this is the inductance value of the new filter, that is the value of L for the high pass filter. So if I know the cutoff frequency omega L, and if I know the cutoff frequency omega H and the value of C, I can find what must be the value of L given the value of R is not varied. That's it. So we know omega L value as 5k, omega H value of 20k, and C is given as 100 pico. So just substitute here and we'll get the value of L. So we'll just see what is the value of L. So on substituting I will get L equal to 100 Henry. Okay, so I need to substitute it with 100 Henry. So here so that is one type of solution, one method to find L. So here we have also done by using the transformation method, that is we can to transform the low pass filter into high pass filter, we need to substitute j omega equal to omega into omega H by j omega. So I will substitute this in the low pass filter transfer function, So if I substitute this, I will get high pass filter function as j omega by j omega n plus omega L omega h into RC. So both are same, like we know the transfer function of high pass filter as this thing, like j omega by j omega plus r by L. So we just need to compare both these terms. So r by L will be equal to this term, and rr will get cancelled, and we'll get L as L equal to 1 by omega L omega h into C. Okay, so in both way you can find what is the value of L. Okay, so basically we just need to compare both the transfer function, and we have some. Hello. Okay.
Sir, please go to the previous slide once.
Which one? Fourth question.
Fifth question, the part you derived.
Oh, I cleared that. So what was the question? What was the doubt? May I know that so that I can
Sir,
clear that?
actually, I missed you wrote the transfer functions for the both,
Okay,
and
okay.
then what you did, I did it.
Okay, okay. I will write here then. I will write it once more. So definitely the low pass filter transfer function will be T of j omega will be equal to 1 by j omega RC plus 1, right? So 1 by j omega by 1 by RC plus 1. So what is the cutoff frequency here? Omega equal to 1 by RC. Okay. So for high pass filter, T of j omega will be given as, from here it's directly clear, right? So j omega L by j omega L plus R. Okay, so I'll bring this R outside, so I'll get j omega L by R by j omega L by R plus 1. So what is the cutoff frequency? Higher cutoff frequency, omega h will be equal to R by L, right? So this is the cutoff frequency of high pass filter. This is the cutoff frequency of low pass filter. So what I did is, like in both the cases R is kept constant, right? So I will substitute this value of R into omega L. So from here I got R equal
Sir,
to,
I can substitute either way, right?
yes,
I can take R from omega L and substitute here.
I didn't get you. What?
I can substitute the value of R from the omega L also, right?
Sure, definitely. From here also I can write. So R equal to 1 by omega L in C. So I'll substitute here. So what I'll get, omega h equal to 1 by omega L C, that is R into L. So what is L? L equal to, so I'll bring L to LHS. So 1 by omega L omega h into C. Okay.
Okay, sir.
In both. Okay, so that's it. So the main thing is, like they have kept R as constant. They have not changed it. So if it is being changed, means we must know what is the value of R. Okay, so that's all about this question. So by substituting this, we'll get L, the inductance L equal to 100 Henry. Okay, now coming to the next question, question 6. So question 6 is a low pass filter is to be hello. Hi, yeah, please tell me.
Sir, actually, any practical use is there to transform this high pass filter to low pass filter?
Yeah, like see, for both Butterworth and Chebyshev. Okay, for Butterworth and for Chebyshev filter, you would have seen the transfer functions to be for low pass filter only, right? The transfer function given, or everywhere the transfer function being defined is only for low pass filter. Have you seen that? Like when you go through that for both band pass for Butterworth as well as Chebyshev, it is all low pass. So how will define Butterworth and Chebyshev for the high pass, band pass filter, band notch filter? How will define? So that is difficult. Like we have to either as other student has mentioned, like we have to remember all those equations, or else, in other words, if I have a low pass filter transfer function, if I know it very well, and if I can design this low pass filter, I can easily transform to high pass filter transfer function, high pass filter, okay, or band pass filter or band notch filter. Okay, so I can easily transform this. So I just need to initially design a low pass filter, and from there I can just transfer to high pass, band pass and band notch filter as a transfer function, and from the transfer function we can design easily the particular
So design,
huh?
then design part it will be like easier.
Correct,
Like that
correct,
you want to say,
correct,
right, sir?
correct, 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 correct.
Okay, sir.
Okay, so like we know like for if I want in passband to be flat, so I need a butterworth filter. So what we'll do, we'll just design a butterworth filter, a low pass filter, and from there we'll transfer that to a high pass. If I want a high pass filter or band pass filter, we can easily transform that to a particular filter. If that is not the
Then
requirement,
easily component
huh?
selection we can do.
Huh?
Then easily component selection we can do.
Correct, correct, correct. Easily we can
I
find the transfer function. From the transfer function, we can find what is the poles and all. From there, we can easily find what must be the component values. Okay, okay,
okay, sir.
okay,
Got
okay,
it.
okay, okay.
Sir, and the other thing is when using the formula, we have j omega equal to omega L omega h by
Huh.
something in the question form.
Correct, correct, correct. Huh.
That how we got, sir.
That is the transformation. You would have gone through sir's lecture. So I have a T of
There also he mentioned direct.
correct, correct. Also for that also it has also been derived
Yes, sir.
in that format.
At
Like
first he took
hmm. For example, like if
at first.
j if I'll check. Okay, so I want 1 by j omega by omega p plus 1. This is a low pass filter. If I want to transfer this to a high pass filter, so how the high pass filter will look, T of high pass filter, it will be somewhat j omega by at omega, some say p dash by j omega by omega p dash plus 1. So the question is like what we need to substitute here, okay, so that I can transfer this to this equation. That's it. Okay, so if I substitute omega equal to the omega L, or here it is like omega p into omega p dash by j omega, we can bring this to this particular equation. Okay, so with the cutoff frequency omega p dash. So in order to we have a low pass filter with omega p, we have to, if I want to bring it to directly to a high pass filter with the cutoff frequency omega p, we just need to substitute j omega. Like for example here this j omega is 1 by j omega. I can easily get it. So if I want to change that cutoff frequency to omega p dash, I have to substitute it like this. So if I so this is just a rearrangement. If I rearrange these values, I can bring it, right. That's it.
Okay.
Hmm? So like if I rearrange
Okay, sir.
this, yeah, this will be 1 plus so if I take both this value, it will be somewhat like omega p dash by j omega. Correct. So I just need to rearrange this value, or just substitute this value here. Okay, so that so in that format for each band pass means low pass, band pass, band notch, everywhere we'll take the general equation, we'll find which value have to be substituted to that particular j omega, so that we can convert this low pass into that particular transfer function. That's it. So maybe it has been done, and we just need to we have just gone through only the transfer function, transformation function, what is the value of j omega that we need to substitute. Okay, so coming to the question 6, uh, so we'll come to question 6. So question 6 is a low pass filter is to be transformed into a band pass filter. So here we need to transform a low pass filter into a band pass filter. So what is the quality factor of the band pass filter? If the cutoff frequency of the low pass filter is omega c equal to 100 radians per second, and cutoff frequency of band pass filter omega 1 equal to 50 radians and omega 2 equal to 5000 radians per second. So we have a low pass filter. I need to transform that to a band pass filter. Given the cutoff frequency of low pass filter is 100 radians. Okay, and what is the parameters of band pass? Band pass that is given as like omega 1 equal to 50 and omega 2 equal to 5000. So like I have a low pass filter, the cutoff is 10, and I have a band pass filter. Omega 1 is the lower cutoff frequency, omega 2 is the higher cutoff frequency. So how to transform? So you know, if P of j omega is a low pass filter, so we'll substitute this j omega equal to q into j omega by omega naught plus omega naught by j omega into this low pass filter transfer function. We'll get a high pass filter, band pass filter. That's it. So what is the value of q? Q is given as, q is the quality factor, so q is given as q equal to omega naught by delta w. Delta w is the bandwidth, that is omega 2 minus omega 1. So this is the delta w. So omega naught by omega 2 minus omega 1, and what is omega naught? It is root of omega 1 into omega 2. Okay, so that is omega naught. So omega naught is given as root of omega 1 minus omega 2. No, root of omega 1 into omega 2. So we have all these values. So omega 1 value is 50, omega 2 value is 5000. We just need to substitute. We'll get what is the value of q. Okay, and if I get the value of q, I have the transfer function. In general, transfer function of low pass filter, I can substitute there j omega equal to this value, and I have q, I have omega naught. I will get the transfer function related to band pass filter. So the question is just to find q. So what is q? Q equal to this omega naught by delta w. We just need to substitute this value of omega 1, omega 2 into this. So we'll check what is the value that we arrived at. So
Sir, how this formula, like j omega transformation, that we need to remember, that's it, or anything else?
No, we just need to remember. So I'll do one thing. Like in next question, you can see why if I substitute that values of q into 1 plus j omega by omega naught plus omega naught by j omega. If I substitute that, we'll arrive at the general general transfer function of a band pass filter. So how you got into means like they have just brought this equation to the low pass function. They have just rearranged that. That's it. Okay. Like for example, yeah. For example, like for band pass, it will take time, but for low pass itself, as I mentioned earlier, like for low pass, it was like 1 by j omega by omega p plus 1, right? So if I take this value outside, so or I will just take high pass filter here first. So I will bring high pass to low pass. So j omega by say j omega plus omega p. Okay, or okay. So if I bring j omega outside, it will be 1 by 1 plus omega p by j omega. Okay, so how I can make this transfer function? This is actually corresponding to high pass filter, right? This is corresponding to high pass filter, but this is similar to low pass filter. So if I write here, it's like 1 plus j omega by omega p. This is a transfer function of low pass filter. So how I can bring either low pass filter to to high pass filter or high pass filter to low pass filter. How I can bring? So I just need to substitute this value, that is j omega by omega p. Okay, so I don't know, this will be equal to this value, so equal to omega p by, so in this transfer function I just need to substitute j omega by omega p by omega p by j omega. That's it. But here since we are also dealing with the cutoff frequency, so we just need to change, say this is p1 and say this p2. Okay, I will just replace j omega by p1 p2 equal to omega p1 by j omega. Okay, so what is j omega? I need to substitute here at low pass filter, j omega is equal to omega p1 into this omega p2 by j omega. Okay, so which means I need to, I will just take another color. So I need to find or write a transfer function of high pass filter, but I have only a low pass filter transfer function, and we know the low pass filter transfer functions cutoff frequency is omega p2, and we know high pass filter cutoff frequency is omega p1. So how I can transform this transfer function to this? I just need to substitute this j omega value. So from here, by this relation, I got to j omega equal to omega p1 into omega p2 by j omega, right? So I just need to substitute the j omega in low pass filter. Wherever there is j omega in the low pass filter, I just need to substitute that j omega with this relation omega p1 omega p2 by j omega. So which means I will get into this relation. That is, I got from I have low pass filter transfer function, I substituted this this relation, and I got to high pass filter. So this is how actually they found what is the value of j omega that we need to substitute into low pass filter transfer function. Okay, in similarly we can find how to find the transfer function of means how to find the transformation from band low pass to band pass. So it is like so this is actually the transfer function of the band pass filter, Tj omega into omega naught by q, this general formula. Okay, omega square plus j omega omega naught by q plus omega naught square. Okay, so how and we have T of low pass filter as j omega, not j omega, sorry, 1 by j omega by omega p plus 1. So if I rearrange in the similar way that I showed for high pass, if I can rearrange these terms so that this entire transfer function we can write in this format, so we can find what is the relation of j omega that we need to substitute there. So we will get like if we rearrange this entire term, I can get a value or the transfer function similar to this. Okay, so you can relate this. So how what must be the value of j omega that I need to substitute? I need to substitute on j omega equal to this value. Okay, so on substituting this, I will get what is if I substitute this in low pass filter transfer function, I will get a band pass filter transfer function. Okay, hello.
So could you please repeat for this case?
Okay, like see the transfer function of band pass filter, okay, is given as j omega omega naught by q by omega square plus j omega omega naught by q plus omega naught square. This is actually the general transfer function of band pass filter. Okay, so if I rearrange, so if I come in this direction, I will get the value of this transfer function as 1 by 1 plus q into j omega by omega naught plus omega naught by j omega. So this is the transfer function of band pass filter. Okay, so I have I have the transfer function for low pass filter. The transfer function of low pass filter is 1 by 1 plus j omega by omega p. Okay, so I have this transfer function. I want to make this transfer function to the bandpass filter transfer function. So how I will do that? I just need to substitute this value, right? This term. I'll just take another color. Okay, I just need to substitute this term with this term, right? Like this is a transfer function of low pass filter, right? If I substitute this term with this entire term, that is q into j omega by omega naught plus omega naught by j omega. If I substitute this j omega by omega p equal to this term, I will get what? I will get the transfer function of bandpass filter, correct?
Yes.
So j omega by omega p equal to q into j omega by omega naught plus omega naught by j omega. So this is how we transform that. That's it. So I have a low pass filter transfer function. Though it is written like this, we'll be getting some value, say 3 plus j omega. Okay. So wherever we can find what is omega p here. So we can substitute that. So 1 by 3, 1 plus. So I need to substitute j omega by 3 with this q into j omega by omega naught plus omega naught by j omega. So we know we will be given the specification what is the cutoff frequency, lower and higher cutoff frequency. We can find omega naught and q. You just need to substitute this term. So this is how it has been derived, like what must be the transformation function to be given over low pass filter transfer function. That is the value of j omega that has to be substituted, so that I will get the transfer function of band pass filter. Okay, so this is how, means like relating these two equation we got. Similarly in the previous I rubbed that for the high pass filter also I showed, right, how it is being related. So we will take both the transfer function of high pass and band pass, not high pass and low pass. We'll arrange the high pass filter transfer function similar to low pass, and we'll compare which term has to be substituted with what, so that low pass will be high pass. So if we relate that, we will get so j omega equal to like omega L into omega h by j omega. So that it must be the value that we have to substitute in the low pass filter transfer function, so that I can get the high pass filter transfer function. You got it. So similarly we can take the general transfer function of other filters like high pass, band notch and all, and we can compare again similar to this, and we can find what is the transformation that has to be done. So this same transformation sir has given. So to transform, we just substitute j omega equal to so and so value. So we just need to substitute and we'll get the value. I think it's clear, right? Okay, so I assume it is clear. We'll go to the next question. Okay, so the previous question, it was to find what is the transfer. Okay, previous question was to find the quality factor, Q factor, and the next question is the same question. Low pass filter is transformed into a band pass filter. Determine the transfer function of the band pass filter with the cutoff frequency of low pass filter omega c is equal to 100 radians per second, and cutoff frequency for band pass filter are omega 1 equal to 50 and omega 2 equal to 5000. Okay, so the question is to determine the transfer function of band pass filter. So the same, either we can substitute in, the values of q and omega naught in the directly in the equation if we know the general the equation of general transfer function of the band pass filter, or we can substitute. So I know the transfer function of low pass filter as 1 by omega by omega p, j omega by omega p plus 1. So I can substitute here the value of means I just need to substitute the transformation function, that is j omega by omega p equal to q into j omega by omega naught plus omega naught by j omega. Okay, and I will get the transfer function. of T of j omega of band pass filter. Okay, so already I have found what is the value of Q and what is the value of omega naught. Okay, I just need to substitute those values and we'll get the relation. So let me jump to the solution itself. So on substituting 1 by j omega by omega c equal to q into j omega by omega naught plus omega naught by j omega in the low pass transfer function, I will get the band pass transfer function as this. That is j means I just need to substitute it and we will expand these values and we'll get j omega omega naught by q by omega square into j omega omega naught by q plus omega naught square. So I know the value of omega naught and q. On substituting, we'll get the transfer function of the band pass filter as this relation. Okay, so I guess it's clear. We just need to substitute those values, and we already have found what is q and omega naught. Okay, so this is the question to find the transfer function of the band pass filter. Coming to the 8th question. So for the question 7, so for the previous question, if the low pass filter is implemented as RC, so the low pass filter, we know it is implemented using resistance R and C. Okay, so this is actually the low pass filter. Okay, then determine the inductance and capacitance values for the transformed band pass filter as shown in the circuit. So a circuit has been given here, and the circuit is like an inductor is placed across the capacitance C. So this is the new filter and it is a band pass filter. Okay, the question is like for the same previous question, if the resistance R is given, so what must be the value of L? Okay, so how will find? So if I just find the transfer function of this circuit, so what is the transfer function? So I already have this R, I have this inductance, so I will just write this as an impedance Z, R and Z. So Z is parallel combination of L and C. So what is Z? Z is equal to parallel combination, so j omega L into 1 by j omega C by j omega L plus 1 by j omega C. Okay, so j omega cancelled. So if I just cross multiply this, I will get j omega into L by C by omega square L plus 1 by C. Okay, so I'll just take this.
Sir, I am unable to see the annotations.
Okay, I think you can't see what I am writing. I mean,
Yes.
I think my net is a bit slow. I will check it. Any other one? Other people can confirm, like whether they are able to see. Not visible. Let me check. Okay. Okay.
It's now visible.
Okay. Okay. Oh, I just cleared it. Okay. Okay. I will start from first. Now it's visible, right? See, it's visible whatever I'm doing, writing.
Yes.
Okay. Okay. I will start from first. So what I will do is like I will just find. I'll draw here. I'll find the transfer function of this this circuit. Okay. So this is R and say this is Z. Z is the parallel combination of L and C. So what is Z? Z equal to j omega L into 1 by j omega C by j omega L plus 1 by j omega C. Okay, so j omega cancelled. I will bring j omega L to numerator. So only j omega into L by C. So j minus 1 square, so 1. So it will be square L plus 1 by C. Okay, so So if I bring L outside, it will be like 1 by C, right? 1 by C by omega square plus 1 by LC. Okay. So what is the transfer function here? So transfer function, if I found the transfer function will be the z of, say, in z by r plus z, right? So z is j omega by c by omega square plus 1 by lc by r plus j omega by c by omega square plus 1 by lc. Okay, so I'll bring this omega square plus 1 by lc to denominator. So I'll get hello, yeah. Square plus omega. So I'll get like r into omega square, right, plus r by lc plus j omega by l. So I can rearrange this.
Sir, here in calculation of z, j into omega l into 1 by j omega c is there. I think there is a minus at my omega square l, right?
Yes, j omega yeah, there is minus. Okay, there is minus here. Okay, so I'll get a term in terms of omega. So I can take this r outside, so it will be like j omega by rc by omega square, and I think I missed something. There won't be r here, right? R is there. Okay, r is there. Okay, 1 pi lc and this is c j omega by rc. So this will be the equation. I can compare with the previous one. So I already know what is the numerator and denominator of the transfer function of bandpass filter that I found during the transformation, right, in the previous question. So this was the equation. So I can substitute here. I think here also I missed that minus value, right? So here there will be a minus. So I'm really sorry for that. There will be a minus term here also. Okay. So already I have got such an equation, and I have got similar equation here. See. So the thing is like numerator is j omega into 1 by rc and denominator is minus omega square plus 1 by lc plus j omega by rc. So if I write here the same equation, like I can write here. So it is like j omega into 1 by rc by minus omega square plus j omega into 1 by rc plus 1 by lc, right? So I just rearrange. Okay, so I rearrange these terms. So this equation I just in order to compare that I have written this here. That's it, the transfer function of that circuit that I found. So I can compare here, right? I can compare here. So if I compare that, so what is 1 by rc? 1 by rc is equal to 4980, and what is 1 by lc? 1 by lc is equal to 250k. Okay, so I know 1 by rc equal to 4980 and 1 by lc equal to 250k. Okay, I think in the question r has been given. So using this r I can find what is c, and using this c I can find what is l. Okay, so so that's how we will solve this question. So we'll see the solution here. I think you understood. So from the previous equation I know the bandpass filter transfer function, and for this circuit I have found the transfer function. So during the same computation that I have done previously, so this is the transfer function of the circuit s by, so instead of j omega I substituted j omega as s, so s by rc by s square plus s by rc plus 1 by lc. So on I can substitute s as j omega. So on comparing this, I'll get 1 by RC as 4980 and 1 by LC as 25K0. So I can get what is the value of L and what is the value of C. So I'll get L equal to 19.92 Henry and C as 0.2 microfarad. Okay, so we have, so here the beauty is like I have a low pass filter, and from there I just transform to a band pass filter transfer function, and I just implemented that band pass filter. That's it. So I could so that is the takeaway of this questions from 6 to 8. So I guess it's clear. Let's clear this.
Yes, sir, clear.
Okay, thank you. So that's all about the question 6 to 8. Now coming to question 9. Okay, the question 9 is, consider a first order active low pass filter. So till now it was like all the components were passive, right? So here we have includes one amplifier section. So we have an active low pass filter as shown in this figure. Determine the value of R1 and R2 and C such that the DC gain of the filter is -50 and cutoff frequency is equal to 200 radians per second. Let R1 equal to 1K. So in the previous questions, if you see, like it's a passive components and the gain will be 1 or below 1, right? And the DC gain. So but here we can adjust that gain. We can have more value of gain. Okay, so we can have more value of gain here using this amplifier session. So how? So the question is to find or design the circuit given these parameters. So how we'll do that? We can easily find the transfer function of this circuit, right? So it's an inverting configuration with feedback is found using this resistance and capacitance kept in parallel. Okay, so we can draw it like invert. Oh, sorry. It is an inverting configuration. So this is Z and this is R1, and I have V in. So the transfer function T of j omega is V naught by V in, right? So what is it? Minus of Z by R1. So what is Z here? Z is the net impedance here. So what is net impedance? Z equal to 1 by j omega C by R2 plus 1 by j omega C. Okay, into R2. Okay, so R2 by j omega C R2 plus 1. So this is the net impedance Z. So I'm substituting this here. It will be minus R2, okay, by j omega C R2 plus 1. So this is Z by R1, or minus of R2 by R1 by 1 plus j omega R2C. So this is the transfer function. So this is the transfer function of the active low pass filter. So it is low pass filter, right? So it is similar to this general equation A by 1 plus j omega by omega p. So what is the cutoff frequency here? Omega p. Omega p is equal to 1 by R2C. Okay, and what is the gain here? Gain is minus R2 by R1. Gain A is minus R2 by R1. So this is the DC gain. So we know it's a inverting amplifier. So what is the DC gain of inverting amplifier? Equal to minus R2 by R1, and cutoff frequency is R1 by R2C. So as we can see here, the gain gain of this filter can be adjusted using the values of R2 and R1, and the cutoff frequency is determined by this resistance R2 and C. Okay, so question is to find the value of R2 and C, right? R1 is being given. So since R1 is given and DC gain is given as minus 50, we can find what is R2. We just need to substitute. Similarly, the frequency omega p is being given as 200, right? So and R2 we found earlier, so we can substitute the value of R2 and we can find the value of capacitance. So that's how we can find these values. So let me show the solution. Okay, so from the circuit, V0 by V is given as minus R2 by R1 by 1 plus SC R2. Okay, so this is transfer function, and at DC DC gain is minus R2 by R1. So we'll find what is the value of R2, and the cutoff frequency is being given. R2 we found, so we can find what is the value of capacitance. So R2 is equal to 50k and capacitance is 0.1 microfarad. So this is the value. So this is how we'll solve this question. So I think it's clear. It's pretty much straightforward and easy question. Now coming to the last question, 10th question. So it's a limiter circuit. So for the limiter circuit shown below, determine the voltage V0. So we need to determine this voltage V0 at which the diode D1 and D2. So the diode D1 and D2 are switched on. So at what value? So V0, this diode D1 and D2 is switched on. Okay. And given the value of R, the value of R is 10k, and the value of R1, R2, R3 and R4. So R1, R2, R3 and R4 is 100k, and the diode on voltage is Vd equal to 0.7. So the question is like values of resistance R is given and the on voltage of Vd is given, that is diode is given, and we need to find what is the value of V0 at which this diode is switched on. So when we analyze this this question, say this is a say this is an ideal op amp. So since this is ground, the voltage here is 0, so this is also virtual ground, right? 0 volt. So at when does D1 get switched on? When there is a voltage drop like this, a voltage drop of 0.7 across D1, the diode D1 is switched on. Okay, so at this voltage, at this point, what must be the voltage here? So I will denote as VA. So VA with respect to ground, so VA with respect to this node must be equal to this voltage. So this is minus, right? So VA must be equal to minus 0.7, then only this diode D1 will be switched on. So at a particular voltage, VA equal to minus 0.7, diode D1 will be switched on, right? So we need to find the value of V0 such that the VA, the value at this point, the voltage at this node is equal to minus 0.7. Similarly, if we check the diode D2, so when diode D2 is switched on, so when the potential drop across this diode is 0.7 here. Okay, so already we know this point is virtual ground. So say this voltage is say VB. Okay, so I need a voltage here with respect to this point must be equal to 0.7. So when VB equal to 0.7, the diode D2 is switched on. So we need to find the value of voltage V0 such that the VB equal to 0.7. At that voltage only the diode D2 will be switched on. So these are the two conditions. So to find or to determine this, we will find what is the value of VA and VB separately. Okay, so from this circuit, so in order to find VA, okay, so we'll assume the D1 is off, and this is R2, this is R1, and this is plus 10 volt. Okay, so this is the output of op amp V0. Okay, so we need to find what is the value of voltage VA here. So how we'll find? We'll just apply the superposition theorem. So while applying superposition theorem, we'll find what is the value of VA due to each of the source. So for example, if V0 is present, we'll assume this to be grounded. So what is the value of VA due to V0? VA will be equal to V0 into R1 by R1 plus R2, right? So this is the voltage here due to V0, and due to plus 10 volt, we need to assume this to be grounded, right? So when this is assumed to be grounded, we can find what is the value of VA with respect to this ground due to 10 volts. So what is that volt? Is equal to 10 into R2, right? This is R2, so 10 into R2 by R1 plus R2. So this is A. So given the value of R1, R2, R3 and R4 are all equal to 100k. So we can substitute this to be all equal, which means this is equal to V0 into 100 by 2 into 100. So V0 by 2 plus again 10 into 100 by 200. So 10 by 2. So this is equal to V0 by 2 plus 5. So this is VA. Okay. So similarly, we can find what is the voltage VB. We'll find what is the voltage VB due to V0 and minus 10 volt, right? Minus 10 volt. So this is R3 and this is R4. So again, we will apply superposition theorem. So when applying superposition theorem, we can find VB. So individually we'll find, so VB due to V0. So we'll ground this terminal, which means VB equal to V0 into R4 by R3 plus R4. So that is due to the voltage V0. And similarly, I need to find the voltage due to minus 10. So I will just ground this terminal and we can find due to minus 10. So if I apply that, it will be minus 10 into R3 by R3 plus R4. Okay, again we know each of these values are equal. R3 and R4 are equal, which means this will be equal to V0 by 2 minus 10 by 2. So it will be equal to V0 minus 5. So this is VB. Okay, so I know what is the value of V and VB now. So we'll find what is the voltage of V0 at which diode D1 is on. So what is so we know the value of VA at which D1 is switched on, right? So that is minus 0.7. So I'll substitute that minus 0.7 equal to V0 by 2 plus 5. So this is equal to minus 5.7 into 2. So it will be somewhat near to 11.4, right? So 11.4. Similarly, if I substitute for what is the voltage due to means voltage at which diode D2 is on. So we know D2 is on when VB equal to 0.7, right? So 0.7 equal to V0 by 2 minus 5. So V0 equal to 5.7 into 2. So it is 11.4 volt. Okay. So these are the two voltage. So whenever the V0 is equal to minus 11.4, diode D1 will be on. So the feedback will be due to D1. So this feedback will contain the effect of this on resistance of D1. That's the result. So from there the output won't be linear. So till that it will be linear. So till that it will be linear. Okay, till that will be linear. After that the linearity will go. So there will be a change in the linearity. So so at V0 equal to minus 11.4, VA will be minus 0.7 and D1 will be on. Similarly, at V0 equal to 11.4, VB equal to 0.7 and D2 will be on. Okay, so this is how we'll find this voltage which was mentioned in this question. I think it's clear. I'll show same solution here. Okay, so hello.
Why these two diodes are to be complementary to each other?
So it's actually the circuit is known as limiter circuit. So I think we have gone through lecture. So usually the output of a inverting amplifier will be like this, right? It will be linear. So with respect to V in, okay, V out will be V in into some amplification. So it is a linear output. So in certain applications we may require to limit the output to a particular voltage. So we use limiter circuit so that the output will be somewhat like this, as if it is being clipped. So till this voltage, say some V1 to some V2 of V in, it will be linear, the output will be linear. After that it will change, it will be either saturated or it will be, there will be a small change, but that will be a non-linear output. So in order to design such a circuit, we require so this is a particular circuit which uh, uh, has this sort of response, like on adding such a diode. So if I have only one diode, means the non-linearity happens only till one direction, right? The other direction it will be, I think it will be linear. Okay, so this is the limiter circuit. I think it's clear, right? Hello?
Sir, I have doubt in that 10 into R2 by R1 plus R2.
10 into R2 by R1 plus R2. Okay.
Why we are adding that, sir?
Like if I consider what is the voltage here, the voltage here will be mainly due to voltage due to V0 and 10, right? This voltage.
Yes.
So if I how to find this, we'll use superposition theorem. So we'll just to find what is the effect of 10, we'll just ground this other voltages to ground, right? And we'll find what is the effect of 10 here. Okay. 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 Okay.
Sir, we should consider that minus 10 also.
Yeah, we can consider minus 10 also. Actually, we should. So if I consider minus 10, we have to ground the other terms, right? So this has been grounded here, this has been grounded. So since these 2 points are grounded, this voltage will be automatically 0. There is no current, right?
Oh, yes.
So there is no effect of minus 10. So that's why I didn't consider this minus 10 during the proof. Okay. Okay.
Sir, I have general doubts to discuss.
Okay.
Sir, if we have capacitor in the circuit, like,
Okay.
could you please draw? I can
Okay.
tell
Okay.
how it
Okay.
is.
I will do one thing. I'll just okay. I'll add one more. Okay. Yeah, I can draw a capacitor, right? Okay, I'll draw a
Sir,
capacitor.
first an op amp.
I have an op amp. Okay. Okay, I have an op amp.
Make now make take non-inverting. Sorry. Connect a feedback resistor
Okay.
between plus and minus terminal. No,
Okay, like
plus
this.
and the output terminal.
Okay. 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 I understood. I just rub this. So you want to
A
connect?
positive feedback.
I connected like this, right?
Yes.
Okay.
And the resistor is connected at this positive terminal and is grounded.
Okay. Okay.
Now at negative terminal, a resistor is connected between the negative and the output terminal,
Okay.
and a capacitor is connected at the negative terminal.
Like this.
Yes, sir.
The ground, right?
And grounded.
Okay.
Let I consider the input is given at the capacitor terminal.
Okay. Here I am going to here or at the ground.
No, sir. No input at all.
Okay.
Let us try to determine how to determine the feedback type of feedback here.
Here the feedback, as I mentioned earlier, the feedback has to be considered based on the voltage attained here at this point and this point. So this is V0.
Okay.
So V0 at this point, what is the voltage? V0 into 1 by SC. Okay. by 1 by C plus, say I will give this as R plus R. So this is the feedback, that is 1 by R plus SCR plus 1. So this is the feedback value, V0 into SCR plus 1.
That is at the negative terminal.
Negative terminal, yeah. And at here is like say this is R1 and this is R2, V0 into R1 by R1 plus R2. So this is a feedback here. So I'll call this beta 1 equal to R1 by R1 plus R2, and this as beta 2 equal to 1 by SCR plus 1. Okay.
Just how to determine the type of feedback here?
So like when which feedback is having higher value, that is its feedback. Like if beta 1 is greater than beta 2, then the feedback is like it is a positive feedback, and if beta 2 is greater than beta 1, it is negative feedback. Negative feedback means that is a feedback. Yeah.
Until and unless we don't know the beta 1 and beta 2 values, we can't determine which type of feedback it is having, right?
Right.
If I take the V0 as a DC value,
Okay.
then
Okay.
how it's going to?
Like yeah, the V0 is DC, right? V0 is DC. So beta 2 will be equal to 1 and beta 1 will be R1 by R1 plus R2. So definitely it will be beta 2 will be high. It is actually negative, right? Negative feedback. Yeah. Hello. Hello.
If I consider the V0 as something like an oscillator kind of output,
Okay.
then how can I determine the kind of feedback then?
I don't know, like how that will be, like definitely this will give somewhat like this output.
Yes.
But I
Yes.
didn't like so we can determine only at this area, right? So at this point it will be totally positive feedback. Whenever this changes, at this changes it will be like beta 2 will be very high. Well, not beta 2, beta 1 will be very high, since this frequency can range to infinity also, like almost all frequencies available here at this transition. So at that it will like beta 1 will be very high. So like the entire this the effect of beta 1 will be very high. Until that, the effect of beta 2 will be uh, higher.
Sir, I didn't get your point.
So like I will got this. So when V0 is high, V0 is high, this is like a DC voltage, say 5 volt. So definitely the voltage feedback here will be lower than this. Correct. But the capacitor won't charge quickly, like it should be 5, but it won't reach that. So due to this resistance, it will slowly it will go to that particular voltage. Say if it is 0, it will slowly it will rise. Okay, till what, like till here beta 1 is like V0 into, so 5 into R1 by R1 2. Okay, so at a particular point this voltage will be equal to this. So okay, so this is like we reached into beta 1, V0 value will reach, like the capacitor will charge slowly at a small voltage, like some small increment in the voltage of across capacitance. Definitely this voltage will be higher than this. Okay, so if this is high, basically it's actually differential amplifier, right? Actually it actually differentiate, the output will be actually difference into gain. Output is actually difference into gain. So suddenly this small change will result in the change in the output V0, so that into V0. So the higher, since this is higher, that positive into V0. So since this is at negative terminal, the voltage will suddenly change. So it will change to minus value. Say if it is 5, this will be minus 5. So if it is minus 5, again this portion is again DC, right? Minus 5. So the voltage that should be here must be actually minus 5 now, but it is now at some beta V0. So again it should actually come suddenly to minus 5, but due to this feedback action, there is a current flowing, and since the capacitor won't change suddenly, it requires a bit time. That is its transition time required. That is the RC time constant. So it will slowly, again it will try to reach minus 5, but before reaching minus 5 it will reach minus beta 1 V0. So again the reverse will happen, that again this voltage will be lower than plus. So again the output will change, suddenly change.
Okay, but I'm asking the kind of feedback. That means you are saying that it will have positive feedback for some duration of time and negative feedback for some duration of time, right?
Yeah, at this transition, yeah, correct.
Okay, that means it
Hello.
is actually depending on the frequency, right?
Yeah, correct. But here,
Sir, but
okay,
actually,
tell me, yeah. But actually it is
in oscillators, we actually say that the feedback is it must have positive feedback,
positive feedback.
right?
Correct.
But here we are saying that it is having both positive and negative.
Mm, that is like in order to make a circuit, we need a positive feedback, right? That is to add up with the input. Like if I have a signal like this, if there is some phase difference, definitely the voltage difference is being amplified. So again the voltage will decrement slowly. Instead I want a summing up, so I just want to make both these in phase, then only it will be added up. So that's why we require a positive feedback circuit.
Okay, but I am unable to correlate these two. I, I think you got my point, right?
Yeah, I understood. Like you want to check whether it is positive or negative, right? If it is only positive, then only it will be like oscillating. So actually that positive feedback is required only during positive feedback there will be the oscillation. But I think
Okay. Okay, sir, I got it. For oscillation purpose only, we are getting the positive feedback. Otherwise, when it is having the stable states
correct,
where that is not required, we are having negative feedback.
correct.
Okay. Sir, and one more thing I want to mention is when we have capacitors in the circuit like feedback networks, how to determine the feedback then whether I can take just V naught as DC and say that it is having like that or anything else.
It depends upon the frequency. Like for example, if I have given simply a DC voltage, definitely it is like this is like open circuited. This will be open.
Okay.
So it
But
is
we actually talk about the out voltage at the output, right?
correct. So it will be like if I connected a DC voltage here, the output will be it is feedback will be open, right? So the output will be like it will be saturated, like whatever is the difference between minus this inverting and non-inverting terminal, that into the gain. So it will be saturated.
Sorry.
So actually you are talking about a capacitor kept at the feedback, right?
Yes, sir.
So I have some circuit like this. Okay, so resistance and say 1 by SC. So it's like 1 by SC by into R. Okay, so actually it's the circuit somewhat like this, right? It's at it depends upon the frequency. See, at 0 frequency it starts from infinity, then it slowly at minus 20 dB it will reduce. So if I give a DC signal, definitely it is like open. So I think like the problem is like if I think you are mixing up with the frequency domain and the feedback, right?
Yes.
I now understood. Like, okay. So like till now we have considered it as like a of s and beta is some constant. So if beta is a constant, definitely it depends upon this beta. If beta, like if beta value is positive or negative, if beta is dependent of frequency, and say beta changes from plus to minus, say beta changes from some plus value to minus value, definitely this feedback the topology can change. Like it can be positive during a particular frequency and can even change to negative feedback in after a particular frequency. If beta is if definitely if beta is dependent upon the frequency.
Okay.
Hmm.
Well,
That's what I think the pole zero concept, I think, like so during some frequency if a circuit is there, like that's what the pole zero concept is all about, right? See, like I have poles here, so if I work at a particular frequency which won't attain at these poles, right, especially these poles, then it is it's actually stable. If it is reaching that particular pole which is at the right side of the j omega axis, definitely it will it won't be won't be stable. So that is like the feedback action itself changes, right?
okay. So, but depending on the frequency, the poles changes.
Huh, correct. Not poles, like depend like poles won't change, poles is fixed, these poles are fixed, right? So depending upon the frequency, if the denominator value of s reaches the pole value, definitely the transfer function, if I write like h of s equal to some a by s plus omega p, s minus omega p. So if I reach s equal to minus omega p, definitely it will go to infinity, right?
Yes.
If that is like y minus omega p, minus omega p means it is on the right hand side. So so similarly, if the beta the like if the if the loop the feedback gain has some dependency upon the frequency, means and the beta changes from some positive to negative, means definitely the feedback topology can change, like from positive to negative. So that's why I think till now we have not considered beta as depend upon frequency, right? In whatever the we have, I mean, whatever sir has taught in that, I think beta is taken as fixed, right? Like some value.
In oscillators, do we need beta is dependent on frequency?
Definitely, like if you see in the RC phase shift oscillator, I think sir has taught about it, right? I don't remember.
I don't know about RC phase shift, but I know about
Hmm.
like mon a stable multivibrator and mono bistable multivibrator.
Okay, so actually monostable stable analog jumps from a particular value to on the right, but in this if I have a frequency dependent so it is minus 180, and this is a feedback, this is a feedback network. Okay, this is actually a feedback network by R and C. So I have V naught and some beta V naught. So this is dependent upon the frequency.
That means we can. I'm generalizing one statement like
Huh, huh,
for an oscillator
huh,
circuit,
huh.
the beta factor is dependent on frequency, right?
Correct, correct. So that's why, like that's what it's all about. Like, so I have a, I have beta, huh? I have summer here. Okay. Okay, so I don't know whether it is, so I simply denote as plus. Okay, so say beta of s varies, with respect to frequency. So only at a, so it is plus minus. Okay, it's plus minus, it's a negative feedback. And for a particular frequency, if the beta is negative, beta is minus, this will be positive feedback, which means if if there is some signal like this, and the signal here will be in phase to this input signal. There won't be input signal, any signal here. We can consider it as a noise or a signal which is proportional to this frequency. So if this get added up, that the signal here will be added signal, and that is being amplified, and this process will go on and will get a sustained oscillated signal. Okay, so for this we must find a frequency at which this beta of s provides a signal here. Say, so if there is no phase here, 1, so if I have v naught, I need a signal which is in phase with v naught. Okay, so that will give a positive feedback signal. So that's we find from here, like at what frequency this in a negative feedback is overcome.
Okay. Sir, one more thing. Let us take a simple negative feedback like A and beta.
Okay.
A is forward path gain and beta is the feedback side.
Okay. Okay. So A, beta. Okay, and I will draw that feedback, right? Okay. Okay.
Sir, here and there is an input.
It's a negative feedback, right?
Yes, negative feedback.
Okay.
For getting for the transfer function here is A by 1 minus A beta, right?
A by 1 plus A beta. Okay.
Now here the concept for a particular frequency, when that means we have the loop gain A beta. For a particular frequency, we are getting the phase as a minus 180 degrees.
Correct. A beta equal to phase of this minus 180.
That means when we are considering the negative feedback and ending with positive feedback, right?
Here it is minus 180. Yeah, correct. That's why it it is getting like if I have a signal here, it will be like some beta into some v naught, and whatever signal is, like it will be somewhat like right. That's why it is getting subtracted.
Subtracted or for this particular frequency, what is the transfer function, sir?
For this particular frequency,
is A by 1 minus.
A by 1 minus A beta. Like if it is angle is 180, right? A by 1 minus. I didn't get you.
Yes, sir. Actually, it is not over. We are going.
Okay. Okay.
A by 1 minus A beta.
Okay.
Yes, sir. Could you please mention that?
Okay. Okay.
Now, depending on the A beta value, how the system is going to behave, sir. If for this value, so for this frequency,
okay,
if A beta is less than 1,
A beta is less than 1. Okay.
If A beta is less than 1 means, that means overall gain is increasing.
Overall gain is decreasing, right? Yeah, okay, okay, increasing, correct.
That means, is my system stable or unstable then?
Like A by 1 minus A beta. Like if this is less than 1, it is like A by, say, like for example 0.9, right? Or 0.5 and all, so it is stable, right? If A beta
Stable. Why you are saying stable, sir?
like less than if A beta is near to 1. Okay, like A beta is coming near to 1. Okay, then this value, the entire value will go to near to infinity. It will tends to infinity. As A beta is less than 1, definitely A by say some value, say like 0.9 or A by 0.8 or A by it will go on like that, like 0.7, like that it will go. So till A by 0.1 it is stable, right? Even at A by 0.001 also it's stable, like some 100 into A.
Okay.
So gain is so if I have bounded input, I have got a bounded output 100 into A again. But if A beta equal to 1, if A beta equal to 1, the denominator is like 0. So that is like infinity into, right, A. So it's not a bounded output. So if A beta is less than 1, definitely it is stable, right?
Set,
Huh. Hmm.
is there any relation between this concept and the Barkhausen criterion?
Yeah, definitely.
Definitely. That means in Barkhausen criterion, the angle must be 0.
Or multiple of 360. So actually what Barkhausen criterion means, like so I have some system A beta, okay, so if there is some signal, so by somehow there is some signal, so in oscillator actually we don't have any input, right? So I have some signal.
We don't have any input, means we just give input and remove, or
No,
how
no,
it
no,
is
no.
gonna.
Like that is actually so if I have a circuit like this, so I have a some RC phase shift a feedback circuit like this. So this actually forms a oscillator. Huh? So this will be an oscillator, like there is 180-degree phase shifted here from this point to this point, and they say RC.
Sir, without having input,
Yeah,
like
that's what I'm
how
coming to
it's.
that. I'm coming to that. So so
Okay.
this is actually a circuit. Okay, this is actually an oscillator circuit. So there is no input here. So how it works? The only input here is uh, the bias voltage. So for every op amp there is a bias voltage, right?
Sir.
The only input is this bias voltage. So I will give some plus 5 and minus 5 volt. Okay, so if so initially it will be off, right? So it will like I'm going to give through some. So I'll give somewhat like this, 5 volt, 5 volt. So this negative polarity. Okay, so whenever I switch on this, or I just connect this bias. So initially it was 0, right? Initially it was 0 till that time, and at a particular time suddenly the voltage changes. From here it is plus 5, and the at negative VCC it will, minus VCC it is minus 5. So there is a sudden change at this particular point. Okay, so this is actually an impulse. This is actually an impulse at this point. So this
Means
impulse,
you are simultaneously giving plus 5 and minus 5, or first you are giving only plus 5?
anyway, like usually it is like it is given through a supply, right? A power supply you will give, so plus 5
Yes, sir.
ground and minus 5. Okay,
Yes.
so whenever
Are you giving plus 5 and minus 5 simultaneously or not? And that's the question.
yeah, simultaneously
Okay.
we'll say whenever we switch on the supply, it will directly both voltages will be available at that point. That's it. So at that point there is an impulse. So if I take what is the frequency response of that impulse, it will be having all it will be having values at all the frequency. That is, if this transition contain all the frequency component. Understood. So which means like whenever I switch on this, this circuit will contain all the frequency components. Maybe like the amplitude will be very low, it may not be very high, the amplitude will be very low, but still there will be very all the frequency will be available. And for a particular frequency, we know like this Barkhausen criterion will be satisfied only at a particular frequency at which this RC, like this feedback, like in this case this is providing 180 phase shift. So this RC phase shift whenever give us a 180 phase shift, at that only the positive feedback will be there. So only at a particular frequency
Sir,
f.
wait.
Huh.
Sir, why 180 degrees you are mentioning?
Like for a like if we are considering Barkhausen criterion, the net loop gain, like from this point if I travel and when I move through this path through the loop, and when I arrive at this point, the entire phase shift must be 360 or a multiple of 360 or a multiple of 0 or multiple of 360. So already I have an inverting amplifier here, right? So here I will get a 180-degree phase shift. So I need a 180-degree phase shift at RC phase shift oscillator, means RC phase shift feedback. So this RC phase shift feedback has resistance and capacitor, so it is totally frequency dependent. So only at a particular frequency, the phase shift of this RC network will be 180, only at one frequency. So that will be somewhere available here. So only that component, like there will be many components, only this component will feedback here. So this will be added again, means this into this gain will get through feedback. I will get a signal here. Again this will be provided through this gain. So this will be continuously I will get a signal like this. Rest all will be attenuated.
Okay.
So this is how like this is why we won't there is we mentioned like there is no input, there is no signal given, or any analog signal or DC separate signal given. That is only bias. Whenever we switch on, there is all the frequency components are available, only that particular frequency component will lead for this loop.
Yes, sir, but the thing I didn't get is by giving impulse, we have all frequencies you mentioned.
Yeah.
I'm unable to get that.
Like if
Like
delta of t, if I take delta of t, if I take what is the Fourier transform of delta t, it is 1, right? Or if I take Laplace transform, it is 1, right?
Laplace transform is
Or even Fourier transform also 1. So what is f? So in frequency domain, at all frequency, like it is irrespective of this frequency, the value will be always 1, right? So the value of this signal will be 1 at all frequency, which means it has all the frequency components. These all frequency components are available. At all frequency, the value will be 1. That's it. Understood? So which so there are like all the frequency components will be available there. Only one frequency will lead to this condition, and which will be again and again added up, and we will get an oscillating signal.
Okay, thank you, sir. You made it clear. But the question is, like in Barkhausen criterion, the characteristic equation is 1 minus loop gain equal to 0, and for the certain frequency, that means it is defined only for positive feedback systems, or
actually it should be positive. That's it. That's the thing. Like if this circuit can act as a negative feedback if the frequency is different. Like if I give a particular frequency, like if this f1 is the oscillating frequency, if the frequency available is f2, it won't be positive, like it won't be oscillating. So the thing is like it should be positive. So how it is positive, that is the answer. Like if I have a signal initially, the same signal I will get here, like the signal available here must be in phase to this. So what is this positive feedback means? Like I have an input signal here. Okay, I have an input signal here, V in. If it is being added with a signal which is in phase to this, it will be added. Otherwise, if I give if I added with an out of phase signal, it will be subtracted, so it is negative feedback. That's it. So in order to get this to be positive feedback, what is the condition? So if there is some signal given here, if it travels through this path and reaches back, it must be in the same phase, then only it will add it up, then only I will get a positive feedback, then only I will get a oscillating signal, which means it should be a positive feedback system.
Sir, okay, sir. And one more thing is, what are the general transfer functions for all kind of filters? Like, that means we have to determine based on the frequencies only.
I think like I don't remember correctly each, like when I showed for band pass, low pass, band pass and high pass, I have shown, right, general transfer function.
Yes, sir.
Similarly, there is for band notch also, I don't remember it correctly.
Okay, sir.
I think you can refer that, like in most of the control system related materials, you can get it. You just type for general transfer function, you will get it.
Okay, sir. I'll try.
Okay.
Sir, thank you.
Okay, thank you.
Sir, I have a doubt.
Sure.
Sir, for a monostable multi-vibrator, what is the meaning of time varying?
Time varying? I didn't get, like we have a monostable multi-vibrator. Okay. So monostable multi-vibrator, you know, right?
The recovery time, sir.
Recovery time is like there is only for monostable. See, I will just tell you. Monostable means it is stable only in one means it has only one stable condition or one stable state, that is the monostable. So it will be like whenever I give a trigger or when I give an input which triggers that monostable, at that time, say for example, if it is if the output is always stable at a particular voltage, if I give a trigger or an input, it will suddenly change, and after a while it will go back to its stable state. Okay, this occurs when there is a change in like there will be some capacitance and the capacitance voltage may change. Okay, during that time only it will be this state is actually unstable state. Okay, later again it will be in the stable state, and it will remain the stable state until there is another trigger. Okay, so I think the term that you mentioned, I think that is related to this unstable state. Okay.
That means the time required
to
for the signal.
For the signal to recover its stable state, I guess so. I too don't remember the correct terminology, so that's why I'm telling. Means that's why I'm mentioning, like it must be.
Okay, sir.
Okay.
Yes.
Okay. So any other questions?
Sir, in the recovery time, what percentage of the capacitor should be charged? I mean, what percentage of the diode voltage should be charged by the capacitor?
What percentage of so it depends upon in which the like the monostable. So I don't remember. It's actually it's circuit. I think it's similar to. I'll just try. Okay, I'll just try with circuit. So it will be somewhat like this, right? And we'll give some sort of trigger here. I guess so. So I think like usually this voltage during the stable condition, it will remain at, say, if this is 0.7, it will remain at 0.7 volt. Okay, and whenever there is trigger, it will slowly the capacitance voltage will slowly decrement to this particular whatever beta into V naught value, and when it reaches beta V naught, it will again the output will again change, say +2 minus or -2 plus, I don't know, it must be +2 minus, right? So it will again -2 plus, so again it will slowly integrate to 0.7. So I think this is the time that being mentioned there. So what voltage it has to be echoed.
Okay, sir.
Means I don't remember. I think if sir has taken, I have not gone through those lectures. So
I saw the voltage would be like beta V naught plus 0.7.
beta V naught plus 0.7. Yeah, correct. Means this plus 0.7.
So the capacitor voltage will be this voltage.
The capacitor voltage will be 0.7. This is the voltage. The capacitor voltage has to change from minus beta V naught to 0.7. That's it. So already it was minus beta. What is the change in voltage in capacitance means this is a change in capacitance, and it changed from minus beta V naught to 0.7. So what is the end voltage? It is 0.7, but the change is like minus beta V naught plus 0.7. That much change has occurred across the capacitor. That's correct. Okay, so I think any other questions? Okay, if not, I think we can wind up. It's already 9:10, right? So if no other questions, means I can wind up. So thank you all. We'll meet next week. So I think one question that I will check. Okay, and I will let you know. So thank you all. Good night.
Thank you, sir.
Good night. Yeah.